Good morning, everyone. It's a great pleasure to have a full lecture theatre again after years of doing lectures for open days into my laptop in my kitchen. So I was about to say it's great to get the feedback. We'll see what the feedback is, but let's assume that it's great to get the feedback. So welcome to Oxford. It's really fantastic to have you all here. My name's Felix. I'm an Associate Professor of Engineering Science. I'm also a Tutorial Fellow at Keble College. This is a really sort of half hour, 25 minutes plus a bit of time for any of your questions, a taster of what some of the things we're doing here at Oxford are. Now, I know on your schedule it says that this is a mechanical lecture. Now, yes, bits of this are mechanical engineering, but one of the joys of the Oxford course, of course, is that it covers all the different branches of engineering. So you'll see bits of chemical engineering in this. You'll see bits of what you might call kind of environmental engineering in this. So already I'm covering 3 different topics just in one lecture, and my work actually spans almost all of the different topics of engineering. But that's enough about kind of the background. Let's crack on. So what I want to talk about this morning is how we can decarbonise transport as quickly as possible. Now, this won't be news to most of you, but we have a problem, right? So we know about climate change, and we know about the links between climate change, but sometimes I think it helps just to look at the data and think about it. So this graph here shows the average temperature of the Earth from about 1850 up to 2016, which is when the most recent data was available when this GIF was made. And this is from a Professor Ed Hawkins. And you can see through the 80s it's growing a bit, and then suddenly we hit this millennium and it takes off. And that trend has not stopped. And why? Because, look, here are the global CO2 emissions in billions of tons with the blue line here on the right-hand axis, and then the concentration in the atmosphere. So we all got quite good at measuring CO2 concentrations during COVID for ventilation purposes. There's a monitor right here on the desk. We're now at about 420 ppm. When I was at school, not that long ago, although for some of you it seems like quite a long time ago, I'm sure, we were kicking around the kind of 330, 340 mark. So it's gone up by nearly 100 ppm, so about 25%. Since really the start of the 90s, start of this millennium, okay? So we know this, we know that we're accelerating CO2. So where does this all come from? So we can apportion where the CO2 in the atmosphere comes from according to different sources. Now, there's loads and loads of ways you can slice this particular pie, right? But this is quite a good one from Hannah Ritchie at Our World in Data from last year. And so we can see that the vast majority of our CO2 emissions, about 75%, give or take, come from energy. And we use energy for absolutely everything, for heating our homes, for moving around, for going to see relatives. You know, you name it, we use energy. And we can break down the energy into buildings, into transport, into industry. And so what I want to specifically focus on today, so my research is mostly focused on the transport part of energy. And this little lecture, I just want to get us thinking about road transport. How do we move around? Now, some of you are probably sitting there thinking, why on earth is this a problem? Right? These are snazzy electric cars. Right? We've invented these, we've solved the problem. They are zero emissions, says so, right on the back of the car. So for those of you who are real petrol heads, you probably can't say anymore, maybe motor heads, this is a Rimac C2. It's got 4 electric motors in. It goes really, really fast, and I imagine if I were ever rich enough to afford one, it would be really fun to drive. More pragmatically, this is a Nissan Leaf. This is an electric car which some of you may have, I don't know, but certainly is one that you're likely to see on the streets. But if you were looking on the roads as you were coming into Oxford this morning, or as you were walking up to the department, how many electric cars did you see? 5%? 10%? 50%? Seems unlikely. So there aren't very many yet. And that's a key point. We know that climate change is accelerating. And we have a solution, potentially. But I think one of the things I want to explore in this lecture is A, how much of a solution are electric cars? And B, are they enough? So let's just think about road transport. So this is what you may think about when you think about road transport, either some horrific polluting truck, probably from the USA, you know, look, you can see all the pollution there, or sitting in a traffic jam. We've all done a fair amount of that. Now, the first thing I point out is, it doesn't actually matter what these vehicles are. These could be petrol cars, could be electric cars, could be autonomous cars. Traffic jam looks the same, regardless of the car. So I think we think at our peril that we have a magic solution, right? Electric cars, going to solve the problem. this problem will still be here. And so if we're thinking about road transport, it's then going to make sense to us to then begin to categorize some of the vehicles on the road so we can split down what the problem might be and then think about how we might want to solve it. So that's what I've done here. So I've broken down all the different types of vehicles that I think are on the roads today into inevitably a whole bunch of acronyms, because that's what engineers do. We love a good acronym. And I've also split out what you might call the powertrain. So a powertrain is a word that we use to describe how a vehicle moves. What causes it to go, effectively? So traditionally, old world cars used an internal combustion engine. Then you've got hybrids. Some of you may indeed drive a hybrid. And then we've got kind of plug-in vehicles. So these are vehicles that you can either at home or at a charging station plug in to charge up. And then we've got electrified vehicles and electric vehicles. And these terms are often used quite interchangeably, but they actually mean very different things. And as engineers, one of our jobs is to try and kind of cut through all the what you might call marketing dress that you put on a problem and actually understand what the technology underlying it is. You probably saw, oh, we're going to electrify everything. Yes, but what does electrify mean? Does it mean actually have it purely electric? Or does it mean something else, like a hybrid? A hybrid's electrified, it's got an electric motor in. But that's maybe not what people think of when they think of an electric vehicle. So we can categorize these things. So I've got a selection of cars up here. So this is a Jaguar F-Type up at the top left. That's a traditional internal combustion engine car. Makes a vroom vroom noise and goes around very fast. Then we've got a Toyota Prius. That's what we call a full hybrid, or FHEV, full hybrid electric vehicle. Okay, so a lot of people will say, my car is electrified because it's a Prius. But it still contains an internal combustion engine. So it's still burning a fossil fuel, at least some of the time. So is it electric? No. Is it electrified? Yes. Does it still contribute to climate change? Yes. So a Prius is maybe a step in the right direction, but it's not a step all the way along the path. Then this is a Mitsubishi Outlander plug-in hybrid. So we've now got plug-in. It's got a plug. You can plug it in at the wall, charge it up. Most people who own these cars, by the way, don't plug them in and charge them up. They prefer to charge them up at the petrol station, okay? Because they still contain an internal combustion engine. And what we forget sometimes as engineers is we develop all these whizzy solutions, but real people, people like me, like you, like your friends, your relatives, all have to use these vehicles. And if we don't make them in such a way that we incentivize using them in the way that we intend to use them, then we make the problem worse. Why is this vehicle worse? Because you've got a vehicle that could run as an electric vehicle, but it also has to tow around some relatively heavy batteries. And if people don't charge it up, all you've done is make a heavier vehicle that now wastes even more petrol when you drive it around. So we have to think about how people use these vehicles. Then we have the BMW i3. That's an EREV, extended range electric vehicle. Electric vehicle, it says so on the tin. No problem. Except, how do you extend the range? You put petrol in it. So, again, it's an electric vehicle, sure, but we're still using fossil fuels and contributing to climate change. And then finally, this is a Renault Zoe at the end. That's one of the many battery electric vehicles that you can now buy. And I sort of term this the degree of electrification. Now, all of these up to this point here, all of these ones here, are still using fossil fuels. They contribute to climate change. Guys, there are some seats down at the front. If you're anything like the undergraduates here, you will hate sitting at the front. But now I've made a thing of it, you're going to have to come and sit down at the front. All of these vehicles will contribute to climate change, provided they're still using petrol and diesel. So the question becomes, what can we do about it? And I think often in engineering, we're always looking for the new solution or the next solution. But it also begs us to look back and look at history. So, everyone thinks electric cars are new, internal combustion engine cars are old. Well, this is a 1912 Baker Electric. This vehicle was the first vehicle to be able to drive 100 miles on an electric charge. Okay, you could buy it in 1912. This is a Mazda 3. It's not a particularly exciting car. I know there have been some other very sort of snazzy Rimacs and stuff up here. This is a Mazda 3. It's a car that, you know, many of you in this room might be able to afford. This car contains the most advanced internal combustion engine in the world. It emits about 25% less than most common internal combustion engine vehicles. This car could do 100 miles 110 years ago. So how far have we really come? I think we need to think about why technology moves in this way. And thinking about history, what we also need to think about is how we can decarbonise quickly. And that quickly is a really important word, because This is the number of electric cars that we sold in the UK in 2021. It's about 6% were battery electric vehicles. Bear in mind the total plug-in number also includes those plug-in hybrids that you can charge at the petrol station. Okay? So we need to be very careful about how we interpret the marketing terminology. So 5%, 6% of vehicles were battery electric sold. And then we look here. The age of cars on the roads. I'm sure you've seen some old bangers, but actually you can assess how quickly what we might call the fleet turns over. So if you buy a new car today, how long before that becomes the average car on our roads? And nearly 30%, 28% of cars on our roads today are more than 12 years old. So even if this number was not 6%, but was 100% this year, 30% of the vehicles, roughly, in 12 years' time, would still contain an internal combustion engine. And this number is not 100%, right? This number is 6%. So I can predict with some confidence that well over 80% of the vehicles on our roads in 12 years' time will contain an internal combustion engine. That's a big problem because of climate change. And those vehicles will still be emitting the CO2. So the decisions we make today are baked in for quite some time. And this is just the UK. Let's think about the whole world. So this is access to electricity. Okay, it's 2019, it's slightly out of date, but I don't imagine it will have changed much, particularly with the pandemic. You can see there are large parts of the world where access to electricity, and bear in mind, access to electricity is defined as the ability to charge a phone or power a radio for 4 hours a day. I think if I had that here, I would not say that I had access to electricity, right? But I definitely won't be able to charge a car under those conditions. So there are roughly 1 billion people in this map, mostly in sub-Saharan Africa, but also in countries like Pakistan, Myanmar, that do not have access to electricity. A battery electric vehicle is not a solution for those billion people. Now, they're not all necessarily driving around in cars themselves today anyway, but they are getting supplies, they are getting food, there is still mobility in those places. And we need to think not just about how we are going to decarbonise our lives, our relatively privileged lives, but also the context globally. And a battery electric vehicle is not going to do that. So we're going to have to think about the old technology and how we can decarbonise that too. So here's the bit where it'll turn into a bit of an undergraduate lecture. If you come and study here, I will give you this slide in about 18 months' time. This is how an internal combustion engine works. And today, about 99% of the vehicles on our roads are powered by this technology. So we induct an air-fuel mixture as the piston moves down. We then compress that mixture. There's then a spark. See a spark plug? What that does is it ignites the fuel-air mixture, forces the piston down, causing some work. That's how we get the power out of the engine. And then we get rid of the combustion products, okay? And there's this nice kind of GIF here. You can see, I'll wait for it to start again. So number one, we're inducting the air that compresses it. The spark goes off, ignites the fuel. We produce the power and then we exhaust it, and we've got this kind of cam arrangement with these valves to make sure that this, what we call the four-stroke cycle, because there are 4 strokes, induction, compression, expansion and exhaust, works properly. Now, all of our students will need to learn and understand, and the very easy way to memorize it is that how it works is suck, squeeze, bang, blow. Okay? So you suck the air in, you squeeze it, it then goes bang, and then you blow it out. I'm sure the giggles are for some other reason that I couldn't possibly understand. Now, that's how we get the power from the engine, okay? But of course, we know that there are harmful emissions that come out of this technology as well. And so key to us understanding how to reduce and eliminate them will be to understand where they come from. So this is now just going to feel a bit like chemical engineering for a second. So we're going to assume that we've got some sort of ideal combustion. So we're going to take some fuel. It's going to be a hydrocarbon. It doesn't really matter what it is. So for those of you doing a bit of chemistry, you'll recognise CXHY as just being some sort of generic hydrocarbon. So it could be petrol, it could be diesel, it could be a biofuel, it could be whatever you want it to be. And we take oxygen, and that gives us some energy, which is how we make the car go, as well as carbon dioxide and water. Fine, no problem there. First problem though, oxygen doesn't hang around on its own. We get oxygen from air. So we're going to need to start to modify this particular equation. So we've still got our fuel here. And now we've got the oxygen, same as before, but we know that roughly, in ratio, the oxygen sits 21% in air, and we can assume that the rest of air is 79% nitrogen. That's not quite true, but as engineers, we're making approximations the whole time, and so this is quite a big one, and so we're going to assume that the rest of air is just 79% nitrogen. Now, no problem, the nitrogen just comes out the other side as well. Fine. Now, you come to Oxford, you want to learn some really kind of key insights. So here's one for you. Combustion is hot. That sounds like a really dumb thing to say, but it has some really important impacts on the chemistry that we're doing here. So the left-hand side of our equation looks exactly the same, right? We've got our fuel and we've got our air. And the first part of the right-hand side, the products of this equation, also looks the same. But because combustion is hot and happens quickly, for example, some of the nitrogen in the air is going to react with some of the oxygen in the air. That forms a chemical compound that we call NOx. So that's made up of nitrous oxide and nitrogen dioxide, NO and NO2. That is harmful. You breathe that in, that will cause, particularly for those of you who might have asthma and other such conditions, that will really affect your breathing. And indeed, there have been recent cases of people whose exposure to NOx has been directly linked to their deaths. There was a girl in South London called Eleanor Kissy Deborah who died explicitly of exposure to this. We also have, for example, some unburnt fuel, some partially burnt fuel. That's because this is happening quickly. If you wait long enough for everything to burn completely in your engine, your car won't go anywhere. We have to do these things quickly to extract the power. And you can replace car with truck, ship, whatever it is. All of these things have to happen quickly. So we can start to apportion these kind of different emissions into different categories. So we've got particulates, we've got pollutants, we've got NOx, carbon monoxide, lots of things you and I really don't want to be breathing. And of course, we can't forget about CO2, the greenhouse gas. Now, I've already done something that I immediately regret, which is I've used the word pollution. And I don't think pollution is a very helpful word, because we see, we need to reduce pollution. But what does pollution mean? So we've now made this assessment of all the different things that can be coming out of our car engine, but we want to reduce them. Which one? Now, easy to say, we want to reduce them all, and that's fine. But do we mean we want to reduce the carbon dioxide because of climate change? Or do we want to reduce the NOx because we're worried about people with asthma breathing it in? All of these things will have different techniques for reducing them. And one of our challenges as engineers is to split these things down and understand how we can make changes to each and every one of them. And the reason I go on about this is we always think that the pollution just comes out of the exhaust pipe. And electric vehicles don't have an exhaust pipe, no pollution, no problem. The problem is that engineers are quite good at their jobs, and it's one of the reasons that I think you're in this room is because you think that engineers can make a difference. And they really can. So this is the amount of a particular type of particulate pollution. So there's a very small kind of bit of soot that you can breathe in the air. And you can see that a couple of decades ago, in the 2000s, about 80%, 75% of this particular pollutant came from the exhaust. And we've all seen vehicles chucking out black smoke. We can believe that, particularly if those of you have ever seen a kind of older diesel Land Rover or diesel pickup truck, you can see the exhaust coming out. It's pretty horrible. Modern vehicles don't look like that because engineers have been pretty good at reducing this. And now the contribution from the exhaust, so this big yellow block in 2022, is probably only about 20%. What we haven't reduced is the emissions from the tyres, the brakes and the road. Every time you drive, the reason you need to replace the tyres on your car, or perhaps mum and dad need to replace the tyres on their cars, is because as you drive along, that friction interface with the road is rubbing the tyres. And what happens? Those bits of tyre come off. They come off effectively as what you might call microplastics. So we think about microplastics in shower gel, might not think about them so much in tyres, but they're coming off and they're going into the environment. And because we've been so focused on reducing the exhausts and doing quite a good job, we've kind of forgotten about this. And when I say forgotten, I don't mean just forgotten, but we actually don't even control it. So this black line here is the amount of particulate matter, or PM, told you we love a good acronym, that you're allowed to emit from a vehicle through the tailpipe in what are the units of milligrams per kilometre. So if you buy a car today, it must meet this criteria here. So no more than 5 milligrams, that's a tiny amount, per kilometre. Here are all the other sources of this PM that are not controlled. So even on a small car, you're emitting about 4 to 5 times the legal limit, at least in this country and in the EU. But if you buy a large car, and by large car I don't mean something like off the scale. This is a kind of 4x4 kind of territory, or SUV for anyone who's an American watching this. You can see that they are emitting about 10 times more from the non-exhaust emissions than they are from the exhaust. We need to really think about where these come from. Now, we've talked about the emissions, and we know that that comes from the fuel, right? We started our whole equation before with that fuel. So why do we use it? It's bad. Why on earth do we use it? Here's why. It's energy density. So most people don't want to stop and fill up their cars every 20 miles, right? It would make driving somewhere really, really difficult if you had to do that. And for those of you who are drivers, you know that if there's a queue at the petrol station, you might get a bit frustrated, even if it's quite a short one. However, we know that diesel and gasoline up here have very, very high volumetric and gravimetric. So volumetric means how much volume it takes up, how big the petrol tank needs to be, and gravimetric is how much it weighs. Okay? And different fuels trade these off in different ways because different fuels have different densities, and we know this. So we can see the traditional fuels up here. So kerosene, that's what they use in jet aircraft, diesel and gasoline up here. Then there's a whole bunch of what we might call alternative fuels that we'll explore in a second. Here's the lithium-ion battery. That's what's in your phone, that's what's in an electric car. This is why it's really hard for us to get rid of fossil fuels, and why so many engineers like me, but literally thousands of my colleagues, are working on trying to get around this. We've got hydrogen. Hydrogen, you may have heard of that being used in vehicles. That's very good on a mass basis. It doesn't weigh very much at all for the amount of energy in it, but it's very bad on a volume basis. I mean, you've all seen kind of how it's the least dense element on the periodic table, so it inevitably takes up a lot of volume. So we've got all these different options. How can we weigh them up? Well, here's a slightly silly cartoon, but I think it illustrates the point. The energy has to come from somewhere. So we've got this kind of chap in a diesel car driving along thinking, I feel like I'm really bad for the environment, and then make it an electric car, move the emissions to the power station, it's really clean. Now, of course, the reality is not quite like that, because this power station could be a solar or wind one, but it's not always. And in the UK, actually, natural gas makes up a significant part of our energy. But we can take this into account. So we can think about the emissions from all phases. So not just from driving the car around, but also from making the fuel, whether that's electricity or a kind of traditional fuel, from processing it, from the raw materials required to go into making the car. And of course, for a battery electric vehicle with lots of batteries in, this is much more substantial, but also how we dispose and recycle the vehicle at the end of its life. At the moment, we legislate on this green box up here, forgetting all the rest of it. This will have to change as we move the technologies forward. And you can make different analyses, so I won't go into details, but feel free to ask me questions. But there are good ways of doing this, and this study from Ricardo in 2020 that showed that you might reduce emissions of the battery electric vehicle by 84% by 2050. Note, that's not zero. We are not a zero-emission vehicle in a battery electric vehicle. Even today, it's an 84% reduction, but that's nowhere near 100. And there are also bad ones. So I'm afraid, I hate to say this in a room full of engineers, but the Institute of Mechanical Engineers released quite a bad study in 2020. So there are also bad ways of doing it. For example, in this study, they just decided to completely ignore how much carbon was emitted during the production, but they still called it a life cycle analysis. That seems like a strange way of doing it. The point of showing you all these different graphs and stuff is that as an engineer, what we do is we train you to do this type of analysis, to spot where people are maybe slightly misleading you. Now, we've said that the problem is the fuel, and we're making changes to that already. So, since September last year, we have doubled, whether or not you knew it, the amount of biofuels in the petrol that you put in your cars today. F1 is going fully sustainable using alternative fuels by 2026. You can run an engine on almost anything. It just needs to have some energy content. And so this here, this red-orange flame, that's an image I took from one of my research students who has been running an engine on this, on gin. Okay? So you can run an engine on gin. Now, you may think that there are better things to do in your life with gin than put them in an engine. It's certainly not cost-effective. At £40 a bottle, I think you may find that petrol is a little bit cheaper. But this is the point. We're continuing to push the boundaries and explore the frontiers of what can be done in the future because we need to decarbonise quickly. And as a sort of illustration of this, you can use both what we call e-fuels and biofuels. So here's an e-fuel, here's a biofuel, where you have got a CO2 neutral process. Will this be in every car? Absolutely not. Battery electric vehicles will take up the majority of the cars that we will drive around. But there's so many sectors that they can't get into. For example, shipping, big trucks. I'm pretty sure if I asked you all to stand up that none of you will be wearing exclusively clothing made in the UK. I'm certainly not, right? We live in a globalised society, and how we decarbonise all of this will rely on some of these technologies. They've got their flaws, don't get me wrong, but we're going to need a lot of different solutions to decarbonise as we go forward. So that's pretty much the end of what I wanted to say, but I did just want to highlight one thing. So this is a student project. So this is from one of my fourth years last year, Sam. He's been doing an emissions project with me. So if you come and study with us, this could be you in about 4 years' time. And he's been looking at NOx, NO2 specifically, one of these pollutants that comes out of cars, and measuring how it moves through the environment. And he set up this nice algorithm, and we got up very early in the morning to stand in the streets of Oxford measuring these pollutants to validate his model. And the nice thing about his model, if I can get the little video to play, yes, is that he can now have a series of vehicles driving up and down this road, right? And you can see the emissions coming out, and you can then pretend to be a person standing at a bus stop or waiting for a taxi or just walking along the street and seeing what your exposure is to these emissions from this validated model. So this is a really nice example of what, by the time you get to the fourth year of our course, one of our undergraduates is doing. And in fact, this project was so good that it won the Institution of Mechanical Engineers prize last year for his project. So that's just an example of the big picture, global context, all the way down to how you, if you come and study here, could be tackling a small subset of this problem in 4 years' time with some of the training that we can give you. So with that, I'm happy to answer any questions you might have, and it's been a pleasure. Thanks for coming and listening.